Okay, so series is just an extension of what we learned last class over sequences. All that a series is, if you take a sequence and add all of the terms together of the sequence, you've created a series. So if you add up all of the terms of the sequence, it turns into a series. That's it. That's the bottom line. And normally, when you're dealing with a series, it's written in what is called sigma notation. That's with this symbol right here. Oh, geez. We use this sigma notation, this kind of like fancy looking E, when we're trying to write a series, when we're trying to notate a series. And this sigma, that symbol actually means summation. It's the summation sign. If you ever are trying to like go into Excel and add up a whole bunch of cells in Excel, this is the symbol used for summing those cells together. All right, so let's go ahead and so now we're going to write what a series looks like in general form. What you do is you write that fancy looking E, that sigma. Then on the bottom of the sigma, you put the lower limit. So we're adding a certain number of terms, right? A certain number of terms in our sequence. Terms numbers 1 through whatever. The bottom number of terms, so say we're starting on term number 1, you would put some variable, sometimes k, is equal to 1. So that means we're starting with term 1, and we're adding all the way up to whatever number is on the top of the sigma. So in this case, n. N is the upper limit, and 1 is the lower limit. Then, after the sigma, you write down the definition for the sequence. So remember last class, we learned how to write definitions for sequences. Like here on part D, this is the definition of that sequence. On part C, this is the definition of that sequence. Part B, this is the definition. We learned how to write down the definitions of the sequences. So after the sigma notation, oh my goodness. After the sigma notation, we write down the definition of the sequence we're dealing with, whatever that may be. So we're just going to write, wow, a sub n in this case. And what this means is we're taking the first term of the sequence, adding it to the second term of the sequence, adding it to the third term of the sequence. And we keep adding till we get to the last term of the sequence, whatever that may be. So let's try it. Here we have a sigma from terms number 1 to 10 with the definition for the sequence being 3k plus 1. And we're trying to add up all of those terms 1 through 10. But we don't yet know what the values of those terms are. So that's what we need to do first, is we need to find the individual values for each one of these terms. To do that, all we have to do is take these term position numbers. We start with 1, that k value of 1, and we plug it into our definition. So 3 times 1 is 3, plus 1 is 4. So our first term's value is 4. That's our a sub 1. We need to repeat this 4, 5, 6, 7, 8, 9, 10, until we get all 10 terms. So I'm going to plug in now 2. 3 times 2 is 6, plus 1 is 7. And I'm adding these together because the sigma tells me this is a series I'm trying to add together. Oh, my line went really crooked there, didn't it? Then I plug in 3. 3 times 3 is 9, plus 1 is 10. Plug in 4, 12, 13. Plug in 5, 15, 16. Plug in 6, 18, 19. Plug in 7, 21, 22. Plug in 8, 24, 25. Plug in 9, 27, 28. And plug in 10, 30, 31. Then I just add all of those values together. And when I add all of those together, I get 175. And that is my summation. That is what my series is equal to. Are there any questions so far? I'm so mad that it went crooked. Okay. But this was a lot of like just lower level math, a lot of computation, right? There's a trick we can do if we have a calculator. If we have a calculator. I mean, I'm sure Desmos does it. And I'm sure that you can Google and say, find the value of a series, and you'll find a website that'll do it for you. But if you have a calculator, what you can do is you can press math, up, up, up to summation. And oh my goodness, there's a sigma. We type in x, so you can change the variable, it's fine. I'm typing in my lower value of 1, my upper limit of 10, of 3 times x plus 1. And I get 175. So all of that work, and I could have just put it in my calculator. So there's a little shortcut using a calculator. I'm sure somebody can figure out how to do it on Desmos. Shortcut in the calc, you press math, and you go to 0 summation. Any questions on that? Oops. All right, so now let's try it one more time in the calculator. This time, notice we're only going from terms 3 to term 5. It's like we're taking the first two terms and we're ignoring them. And we're only adding together 3, 4, and 5. So I'm going to press math, up, up, up to summation. X equals 3 through 5 of 1 plus x squared. And you get 53. And this checks out. When I plug in 3, that's 10. When I plug in 4, that's 17. When I plug in 5, that's 26. You add those together and you do get 53. All right. Now the hardest part is when they do not give you the definition of the sequence. So yes, what we learned last class, we do need to apply today. We first need to figure out, okay, what is the definition for this sequence? So, what pattern do you see? Yes, we're just increasing by 3 every time. Plus 3, plus 3, plus 3, plus 3. Meaning that this is arithmetic. So I can use my formula a sub n is equal to a sub 1 plus the common difference times n minus 1. This is what we learned last class. My first term in this case is negative 2. My common difference is 3. And it's multiplied by n minus 1. Now I'm just going to quickly simplify this down. Whoops, no, what the heck? Minus 3. And it becomes 3n minus 5. That's the definition of my sequence. So when I'm writing my series, I'm going from term 1 to term number 5. And my definition is a sub n is minus, oh God, no, 3n minus 5. And then either you can just take these 5 numbers and quickly add them in your head, or you can use your calculator and enter this in. So we have 1 to 5, 3n minus 5. Now we get 20. Any questions on that one? Okay. So then, let's try it again. Use sigma notation to write the given sum. So we need to figure out what the definition is first here. Or rule, you could say. What pattern do you see happening? We are increasing by 5 every time. However, sometimes, yes, Maddie. Sometimes it's easier to try to think of this, these sequences as not arithmetic, because with arithmetic we have to do all this, right? What we did above, we have to plug it in, simplify, blah, blah, blah. But if you try to think of the relationship between the term value and the term number, sometimes it makes it easier to write down the definition. So notice the relationship between the term and the term number here. What do you see? Like Maddie said, they're just multiples of 5. What are we doing to the term number to get our term value? We're just multiplying the term number by what? 5. The definition for the sequence is just 5n. Yes, if that problem solving is too much for you, you could have just done the arithmetic using this formula we learned prior, okay? Then we write down our sigma. We're going from term number 1. Our definition is 5n. What is our top term number? Bless you. Yes, Maddie, how'd you get that? Maddie's on fire today. You drink some coffee? Yes. We take 250 and we divide it by 5 because we just multiply the term number by 5 to get the term value. So we just go backwards from, oh gosh. We go backwards from 250 to get our term number by dividing by 5. And our top term number is 50. So then, this is where a calculator comes in handy, because it would be really annoying to find all 50 terms, right? Well, We don't have to. Whoops. 1 to 50. 6375. Any questions on that one? All right, let's try one more. Remember last class I told you that when we're trying to define sequences that have fractions, it's easier to think of them as separate numerators and denominators. So, how can we define the numerator here? How can we define the numerator? Yeah, numerator is always 3. Thank you, Kaylin. Now the denominator is a little tricky. Yes, we recognize that we're multiplying by 10 every time, right? But should I just put 10n? Would that give me my correct denominator? Let's try it. Let's try plugging in 2. When I plug in 2, 10 times 2 is 20. Is that what it needs to be? What should I do with the n? Remember when you're multiplying, it's geometric? Do you remember where the n was in geometric? Yes, yes, Colin. I think you have the right idea. It's in the exponent. It's in the exponent. So now let's check it. If I plug in 2, 10 squared is 100. What about when I plug in 3? 10 cubed is 1,000. Oh, that's what I wanted. Okay, so I do have the correct definition now. So now, you guys did that really well. My other classes struggled so hard on that one. Okay, so now let's go ahead and write down our series. We're starting with term 1, going to term 4 of 3 over 10n. And when I put that in the calculator, it just gives me 0.3333 actually. Any questions on this one? This is why students find sequences and series so hard, is because there are so many different types of sequences that you deal with. And there isn't really a set way to do them all, right? There's just many, many different ways that you have to problem solve your way through them. And sometimes you guys struggle with that. Okay. So now, sometimes, and I want to go over this because it is a question on your Math Excel. Sometimes they will give you series where every other term is negated. So here you see we're looking at 2 series. The first one has the even terms negated. The second one has the odd terms negated. Negated, by negated I mean they have a negative in front of them. Now, if we were just trying to write down this sequence, we couldn't do it, right? There's no way. This isn't just a true sequence increasing by the same amount every time. But we can write this series by using this little trick. If the odd numbers are negated, when we're writing down the sequence, the series, from terms number 1 to 4, notice these are the same term values as the problem we just did right up here. So the definition remains the same, 3 over 10n. But because every other odd term is negated, all we do is we put negative 1 to the power of n in front of our definition. And this makes every other odd one negative, which is incredible. I put this in my calculator and I actually get negative 0.2727. If every other even term is negated, start out the same way, but in front of my definition, I'm going to put negative 1 to the power of n plus 1. This will make every other even term negative. And putting this in the calculator, I get 2.2727. Any questions on this just very, very small occurrence? That's just a little trick you can do. Someone somewhere at some point discovered this, and it's just, it's kind of cool, so they like to ask this question sometimes. Yeah, right? Okay, so now, and you're going to love this. If we were in school, I would fully have to teach you this page. Because if we were in school, we would make you do these things without a calculator. We would make you find the sums of these huge sequences without a calculator, which finding like 90 terms in a sequence and adding them together is ridiculous. So what they did was, if we have an arithmetic sequence, they created this formula to find the sum if you don't have a calculator, so that you don't have to plug these things into a calculator to get your answer. You can just use this formula. But because we are not in school and we're virtual, you always get a calculator, so you can just always plug it in, or you can always use Desmos, whatever. Okay? What? Well, I wouldn't really say it's harder, because finding the sequence in and of itself is kind of hard, but anyway. So that's for arithmetic. For geometric, this is the formula that you can use to not use a calculator. But because we are not in person, you can just literally plug in the summation. Plug in the summation. Any questions on that? Any questions in general? Do you feel good? Do you want me to do another example? I will take silence as a yes. You would like me to do another example. What'd you say, James? I do. So in this one, we're trying to, again, write the series, but first we have to know the definition of the sequence. Whoops. So Oh, it's not erasing. Okay. So, what is our numerator always? 1. So we can define our numerator as 1. What about our denominator? Now, oh, I do want to say this. Because we're treating this as a series, remember I said we don't have to start on term number 1. So if I don't have to start on term number 1, and I instead say we start on term number 3, what is the value of that? What do you now recognize is the similarity between the term number and the term values exponent? What do you notice? So if I make this term 1, term 2, then I'm starting on term 3. My denominator is always going to have a base of 5, but what do you notice about the exponent? So look at the term number on this first one. The term number is 3, right? That's our third position. The term values exponent is what? It's also 3. On the next one, the term number is 4. What's the term values exponent? It's also 4. So what that means for us is that our exponent is just equal to the term number. My exponent is just n. N represents the term number. So then when I'm writing my sequence, I'm going from, now remember I said I'm going to start on term 3. What term number do you think I'm ending on? Yeah, I go to 15. So then, when I plug this in my calculator, I actually just get 0.01. Any questions on that one?